So without further ado, let me introduce to you Dr. Clara Sousa-Silva.
All. That's all true. But I am also a quantum astrochemist. And what that means is I study and simulate the quantum behavior of molecules as they interact with light in space. And so, space, astro, molecules, chemistry, quantum. And that's a really big title for what I do, but my goal is easier to understand. My goal is to one day identify life beyond Earth. And I'm aiming to do that by studying all potential signs of life, even the really weird ones, wherever they may be. Now, in my line of work, I find myself often thinking about my alien colleagues. I imagine an alien astronomer somewhere out in the galaxy looking for life in their night sky. Now, if this alien astronomer pointed their powerful telescopes in our general direction any time in the last 100 years or so, they may have heard us here on Earth, clearly full of life. Without even meaning to, we have been sending signals, radio signals, for over a century into the galaxy. We've been sending TV signals since our first television broadcast in the 1920s. And so any alien species that's been listening in at the right frequencies could have heard us and know everything about our messy history, our politics, our entertainment choices. These messages that we inadvertently sent out to the galaxy have long left the solar system. And any alien astronomers on any planet or moon within this sphere you're about to see will have been able to hear us. But what if we went really quiet? If the whole world stopped sending out radio and TV messages? And that's not that crazy an idea. Plenty of very smart people think that we shouldn't be advertising our location to the universe where nefarious alien species might hear us. So, let's say that at this point, no alien civilization has spotted us yet. We got lucky. And now we all collectively go very quiet. Could an alien civilization still find us? The answer is yes. Any alien astronomer worth their salt, and I like to think highly of my alien colleagues, would be able to still know we're very much here. Let me explain. They could look at our sun and split its light into a rainbow. And if they did, this is exactly what they would see. They would see our sun's imperfect rainbow. The imperfections you see here, these shadows, happen when some of the light from the sun is absorbed by atoms and even molecules from the colder regions of the sun where they can survive. And they absorb some of the light from the sun. And we call these absorption lines. And that happens because atoms and molecules behave in a very unique way. Molecules still have to follow the laws of physics like everyone else, but these aren't quite the same physics we are used to. Molecules are so small that they have to obey the laws of quantum physics. And one of these very important laws is that they can only absorb quantized amounts of energy, which correspond to specific wavelengths and therefore specific colors of the rainbow. And so these alien astronomers could look at exactly this picture, this rainbow, and using their universal knowledge that they got from their own quantum chemists, know exactly which molecules and atoms were causing these lines in the sun and figure out its composition. Then, if they were very patient and they were fortuitously aligned, they would notice that every 12 years, a few new lines would appear and then they would disappear. And every 12 years appear again, and these new lines would be due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun. An alien civilization with only slightly better technology than we have now would be able to study these new lines and know that Jupiter has a huge complex atmosphere with not just hydrogen and helium, but methane and ammonia, hydrogen sulfide, and many more gases. And if they had technology that is only a few decades ahead of us, they would be able to notice that every year a few much fainter lines, too faint to see here, would appear. And these, of course, would be due to the Earth's atmosphere as it crosses in front of the sun and absorbs more of the sun's light. The way they would actually observe this, Zach? The way they would actually observe this is by separating the sun's light into different colors or wavelengths and seeing how those different wavelengths change as the Earth and its atmosphere crosses in front of the sun. You can think of our atmosphere and its light as a planet-sized message, communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute an awful lot. And those alien astronomers will be able to know that on Earth, we don't just have an atmosphere like Jupiter. We have a biosphere, and we can do the same to them. Now, first, we do have to find the planets themselves, and we've been working on that for a really long time. We have known about Mercury and Venus and Mars and Jupiter and Saturn for thousands of years. And we observed them with early telescopes on or before the 17th century. Then we discovered Uranus in 1781, Neptune in 1846, Pluto in 1930, and then we lost it again in 2006. And then we found our first planet around a star other than our own, and that was called 51 Pegasi b, this one right here. From then on, we kept finding more and more planets. We have become very good at detecting planets with many different methods and many different telescopes. What you see here appearing on the dome are all the planets we have detected beyond our solar system. The different colors tell you the different methods we've used to detect planets. For example, the technique I just described that lets you see inside a planet's atmosphere, that's called transit. And you'll see all the red dots. Initially, we didn't have many. Then we had a telescope called Kepler that just pointed at one bit of the sky, hoping that it would be somewhat representative of the entire night sky, and really focused on it and detected thousands of planets. Since then, we have had more dedicated telescopes that can detect more planets. In 2018, the TESS mission launched and discovered tens of thousands more, also using a transit technique. Radio velocity is very useful for very big planets. It's what we use to detect planets that are so big they make their own star wobble. We are getting better at that, and now we can detect smaller and smaller planets with that method, but it's still really difficult. What I want to point out is imaging. The ability to just look directly at a planet is still quite rare. There's very few blue dots around you, and that will remain true for a very, very long time. Stars are bright, and we can barely see most of them, even in our galactic neighborhood. Planets are even dimmer, so very hard to look at directly. So we have found the planets, we can do that. But what are these planets like? We have found planets with similar sizes to Mars, Earth, and Venus, and a little bigger. A type which we don't really have in the solar system. They're called super-Earths or mini-Neptunes, and they're just significantly bigger than the Earth, but smaller than Neptune, and they seem to be extremely popular throughout our galactic neighborhood. And we're only just beginning to understand these weird medium-sized planets. But we have also found Neptune-sized planets and even more extreme planets that are like Jupiter, gas giants, but sometimes, in fact, quite often, we find them not where our Jupiter is, but where our Mercury is. And they're so close to their own star that they are so hot, and these are intense planets. So we know there's a huge diversity of planets out there, but we've only just begun to understand them. Specifically, we've only just begun finding atmospheres on these planets, and we still know very little about them. Now, future missions will provide more data on more planets and their atmospheres, which means we are on the cusp of being technologically able to detect signs of life. But when thinking about detecting life, how do we know what to look for? Well, we can start by looking for planets in what we call the habitable zone. The habitable zone is the bit in any solar system where you're not so close to the sun that you just boil, and you're not so far from the sun that you just freeze. In the solar system, Venus, Earth, and Mars are just about in the habitable zone. But that's because we have a pretty big star. The system you see here on the dome is called TRAPPIST-1 system, and it has many planets, which you see here orbiting, and it has 3 of them in their habitable zone. But this star is a brown dwarf, and they are very small, very dim, and not very bright. So for these planets to be in their habitable zone, they have to have orbits not of a year like we do, but what about 6 to 12 days? And because their orbits are so small, their habitable zone and actually all the planets in the system would fit within the orbit of Mercury. So this is a very cute, very compact system that still has potential for habitability. But even if a planet's in a habitable zone, like Venus and Mars, it isn't necessarily inhabited like Venus and Mars. So how do we make sure that an exoplanet, even one in its star's habitable zone, is indeed habitable? And can a planet be habitable but not inhabited? Well, we know that the laws of physics are universal. We also know that chemistry is universal. We have tested many of these physical and chemical boundaries of the universe, and so we know. But what might be the universal laws of biology? We can start with what we do know. We may know nothing about what aliens might look like and like to do, but we can make some really good guesses about some things they must do. They may be very different from ours, but they still have to make use of the same physics and the same chemistry that we do. And there is a large but limited number of elements from the periodic table that alien life can use. And as such, there's a limited number of molecules that it can assemble and release into its atmosphere. On Earth, all life does that. All life metabolizes and produces gases. And these gases are made up of thousands, literally thousands, of small molecules. Alien life would similarly be expected to produce thousands of molecules. But what molecules do we look for? Now, detecting any molecule in the atmosphere of an alien planet is very difficult because most molecules are only able to influence the atmosphere in very minor ways. But we do already have the technology to detect a few molecules on a few types of planets. So, when we do, how do we know which molecules might mean life? For example, we could look for molecules that we know life on Earth produces, which we call biosignatures. But that doesn't necessarily help us because we could look for ozone, for example, and that is very much a sign of life on Earth, a secondary product of photosynthesis, so a sign of plants. But ozone is also sadly produced just with the radiation from the sun reacting with naturally occurring gases and water. Or we could look for methane, definitely a sign of life on Earth. But sadly, methane is also produced not just by cows, but other non-biological processes like volcanoes. Okay, what about nitrous oxide? It is produced by bacteria and algae, but sadly also produced by lightning, which we know happens on other planets. And this is true for almost every molecule that life loves to produce. They are also produced by non-biological sources. We call this a false positive problem. And it sounds like a cruel astronomical coincidence, but it isn't. This false positive problem happens because these molecules are lovely, but chemically speaking, they're quite easy to make. And so life makes them, but not life also makes them. Which means detecting any of these molecules by themselves on an alien planet wouldn't necessarily indicate life. Now, there are two solutions to this false positive problem. One is to consider context. For example, oxygen on its own might not be a good biosignature. For example, if our sun had different levels of radiation, or if our oceans were evaporating from a runaway greenhouse effect, or if trace gases in our atmosphere, like methane, weren't there. Then oxygen could accumulate in our atmosphere without any need for life. But in the exact context of our planet, our sun, and the other components of our atmosphere, like methane, oxygen is a robust, wonderful biosignature. So if we can get context for the molecules we do find on an alien planet, perhaps we can find a promising biosignature. The issue is we're not quite ready to do that because we're not ready to detect most molecules on most alien planets. Now, life as we know it is likely one island in the vast archipelago of possibilities for life. Our galaxy has a huge diversity of stars, and orbiting them are planets of every kind. Earth alone has given rise to billions of different species. So it's not a big leap to think that life itself can arise in a large array of unexpected forms, and that life will have many strange biosignatures beyond those that we are used to considering. But if we want context, we need to know what about 16,000 molecules look like so we can spot them on an alien planet. And right now, we're currently only ready to detect about 4% of them. So there's over 15,000 molecules we can't yet detect. So all these extraordinary biosignatures that require context, we can't solve that problem. Which brings me to the second solution to the false positive problem. We can instead look for molecules that, although are less obvious, like oxygen, but are biosignatures with very low or no false positives for life. An extreme example of this would be complex pollutants and other signs of industrial activity, like city lights, though that's obviously an edge case. CFCs on Earth now don't exist in large quantities, but for a while, things were looking pretty grim. We had a lot of CFCs in our atmosphere, destroying the ozone layer, and any alien astronomer that saw us would know we're here, and we're idiots. And I would like to think they've been very proud of how far we've come, reducing CFC usage, shrinking the ozone hole, and I would like to do the same for them. But I don't really want to rely on my alien colleagues polluting and destroying their planet for me to be able to find them. And so my favorite, marginally less extreme example is the phosphine molecule. Phosphine is a very strange biosignature with extremely low false positives for life. Now, when I first started working on phosphine over about a decade ago, it was very much not considered a good biosignature. In fact, no one really knew about it, and those who did knew it for only two things. One, as a marker for violent storms on Jupiter and Saturn. Phosphine is detected in the upper layers of these planets, but initially it was a really surprising thing to find on Jupiter and Saturn. And that's because the temperature and pressure in these planets are way too low for the formation of phosphine to be something that just happens. But the answer here is these planets have hellish depths where it is hot enough for phosphine to form. And then phosphine is aggressively dredged up to the top through the observable layers, surviving to much larger concentrations than we would otherwise predict, which is really interesting, but nothing to do with life. But the other reason anyone thought to think about phosphine was because phosphine is also a highly flammable, extremely toxic, and outrageously foul-smelling gas. It interacts fatally with our oxygen metabolism, and so it's a really effective killer, which is why it's widely used as a fumigant and sadly, why it was used as a chemical warfare agent in the First World War and most recently by ISIS. It is also emitted to the Earth's atmosphere as an unfortunate byproduct of methamphetamine production. So, pesticides, war, meth, definitely all unequivocal signs of life, but not necessarily what I would expect or hope aliens would engage in. So at this point, phosphine still didn't seem like a particularly promising sign of life, just a rather scary one. But as I was researching phosphine, I realized that for about 100 years now, there had been quiet but regular mentions of phosphine being found everywhere, which was very much unexpected because on rocky planets like the Earth, phosphine is really hard to make. We don't have the extreme places that Jupiter has. When it is made, it is so toxic to life. And even then, it is so reactive with the Earth's atmosphere that it gets destroyed almost immediately. So we shouldn't see it anywhere. And yet, we do. We find it in trace amounts ubiquitously throughout the globe and in weird places in strangely large quantities. Places like sewage, marshlands, rice fields, lake sediments, the intestinal tract of fish, the intestinal tract of babies, the feces of penguins, the farts of badgers, and actually, the intestines and excrements of almost all animals that we've bothered to check. And the one thing that all of these ecosystems have in common is that they're all anoxic. They're without oxygen. These are biological niches that are populated by anaerobic life that doesn't rely on oxygen. And phosphine is only dangerous to people who like oxygen, like us. But these environments exist, and they're poorly studied, and here phosphine is not so toxic. It's not so evil. It is only phosphine's relationship with oxygen metabolism that makes it so toxic. But for the majority of time that life existed on Earth, it didn't rely on oxygen. And so other planets with life less oxygen-loving than our own could happily have phosphine as a biosignature. So my team and I simulated thousands of hypothetical planets around hypothetical stars. And then we looked at what JWST, a mission that has now launched, could possibly see. And we found that it would be difficult to detect phosphine on Earth-like planets around Sun-like stars, but possible. And it would be really easy to find phosphine on planets around small stars like the TRAPPIST system we saw earlier. And this made phosphine quite promising as a biosignature. But what makes phosphine really appealing is that it seems to have no false positives for life as long as it's found on a rocky temperate planet, so not a sign of life on Jupiter. And we figured this out by looking at whether phosphine could be made just spontaneously through normal chemistry, and that was a no. So we thought, okay, what if a comet hits really fast, really hot? Could you make phosphine? No. What about a volcano, like methane? No. How about lightning? And there we can make tiny amounts of phosphine, but not enough to detect it anywhere. We consider more and more extreme potential avenues for making phosphine, and other than life, we couldn't come up with anything. So at this point, phosphine seemed like a really reliable sign of life. So is that it? Could we just look for phosphine in the galaxy? Not quite. For example, a few years ago, I joined a team of scientists that made several observations with different instruments months apart that seemed to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable place on that planet. And the notion that phosphine, a molecule I had claimed to be an extremely promising biosignature with low false positives for life, might be present next door was of course very exciting, and the press thought so too. But before we jump on life as an explanation, I should point out that there's still much about Venus we don't understand, and all we really know is something weird is happening there. And currently there's plenty of controversy surrounding this observation, and that's not surprising. Any detection of life will be made at the very edge of instrument capabilities, even very good instruments. The original observations we made were with ALMA and JCMT, two extraordinary telescopes. But finding life will always happen in a noisy, delicate place. Currently, I'm on research teams that both find and don't find phosphine on Venus, and neither team is doing anything wrong. This is just very difficult and uncertain work. And right now, we still don't know if the signal is real, if it's unambiguously phosphine, and if it is phosphine, what or who is making it. But what I want to highlight at this point is how a virtually unknown and quite unusual and disgusting molecule became such an important piece of the puzzle in the search for life. And phosphine is just one molecule. Venus is just one planet. Even if it turns out we indeed have found phosphine on Venus, this won't be the last time that we will find a potential sign of life on a planet beyond ours. So the question is, how do we become better prepared to interpret such a discovery next time? And that's what I spend most of the time towards. It's never going to be as simple as detecting an interesting molecule on an alien planet, because as much as I like phosphine, and I do, and as much as I like the more traditional biosignatures that won't kill me, like water and oxygen, which I do, we will not be finding life with a single molecule. As the Venus story shows, the detection of life will likely be uncertain. And all we can hope for is to slowly, painstakingly reduce that uncertainty until life is the only explanation that we have for what we see. But that uncertainty will only be reduced if we are willing and able to both detect and understand more molecules, even if they're not pleasant or abundant. And right now, we're missing thousands of molecules that we still don't know how to detect. But to find life, we have to be willing to consider this big picture, all the possible molecules that can together help us get a holistic view of an alien biosphere. Right now, my biggest professional concern is not that we will fail to look at a habitable planet in our lifetime. My biggest professional concern is that we will very soon point our telescopes directly at an inhabited planet and just not have the tools to know it. And today we're not quite ready to both detect and understand the potential alien biosphere, but we have never been this close. With the recent launch of JWST, as well as the telescopes of the next decade, like GMT, which will be on top of Mauna Kea, dedicated to finding oxygen, and Ariel, which will look at thousands of planets' atmospheres. For the first time in the history of humanity, we will have the tools to detect life beyond our sky, if we know what the molecules look like. But there's a lot of work to do. For example, take phosphine. We know how to spot phosphine in the starlight that could go through an alien atmosphere, but that's because I spent my entire PhD simulating how it interacts with light. But phosphine is just one of those thousands of potential biosignature gases. And I would love to repeat my work that I did for phosphine to learn how to detect these thousands of molecules. But I'm just one person. And to do phosphine, a single molecule, took a lot of sweat and tears and supercomputers and 4 years of my life and very, very patient housemates. Which means if I was going to work on those 15,000 molecules that were missing, it would take me over 60,000 years. This to say, I will need help. There are billions of stars in our galaxy alone, with billions of planets orbiting them. And these planets could contain trillions of life forms, releasing thousands of molecules in their atmospheres just waiting to be detected. But this is all much more work than I or the current cohort of scientists could possibly handle. And looking for life is a necessarily interdisciplinary, collaborative science. We definitely need astrophysicists and engineers and biochemists and quantum astrochemists. But when the time comes, we will also need philosophers and poets and lawyers if we're ever going to make sense of it all. So I'm thrilled to be here, particularly because I suspect everyone in this room could one day contribute to this project, so that one day, very soon, we may point these bigger and better expensive telescopes at a potentially inhabited planet and learn that we have at last found life. Thank you.
All right, thank you so much, Dr. Clara Sousa-Silva. So we do have a couple of minutes before we need to vacate the theater for the laser show. So we're going to try something different. We're going to put up a QR code and ask you to type your questions into the questionnaire. And then Maya on our team will be reading off the questions from the back of the room to our wonderful presenter. I'd like to also thank, as we're getting that set up, Zach for doing his usual fantastic job as running the board for all the visuals, and the audio-visual team as well, who are always here for us. Maya, do we have any questions yet?
Not yet, but while people are getting them in, I have a question. Is there a particular molecule that we haven't been able to detect yet that you would be excited to see where it exists in space?
It's a great question. Yes, there's a collection of molecules called hydrocarbons, so just simple C's and H's, hydrogen and carbons. And often you get these rich, complex hydrocarbon atmospheres like Titan, and we don't yet know how to tell them apart. And so we can detect some, sometimes all, but we can't know which of them there are. And so it's a whole giant family. The good news there is that they're very important for the petroleum industry, so there's money in the work. But the bad news is no one is doing it yet. But that would be my next step.
Thank you so much. All right, we do have some questions now. The next one is, are there any promising methods being developed for molecule detection, possibly for organic molecules?
Some, there's like 12 people in the world doing this. I know them all. We're all friends. But this is often considered just really fundamental work that people just presume has been done already. People are always surprised by the notion that we don't know what these molecules look like. And so the combination of it sounding like quite fundamental and being really hard work means it's hard to fund and it's hard to get people to want to do it. And so I ran a program in a North London school where I got high schoolers to help me. And I had a team of 15 kids working with me. I split them into 3 teams, Team Titanium Oxide, Team Methane, and Team Acetylene. And they published papers, peer-reviewed scientific papers. And they're all my co-authors. I've got now hundreds of children as my co-authors, all working on this project. So things are getting better.
Thank you, awesome. The next question is there any promise in looking for direct radio transmissions like the ones we've sent out?
Yes, we look at them all the time. We're always checking when we look for phosphine or methane or the others I mentioned, acetylene, titanium oxide. We also look at the radio, but so far nothing. But we have only been sending these messages out for a blink of an eye in astronomical terms. And so even if they're happening, it could easily be that we're all ships in the night missing each other. And so my goal is to focus not on finding the most exciting life possible, aliens I could be friends with. I'll take like alien grass happily.
All right, so the next question is, could there be molecules that we have never discovered that we wouldn't know about or be able to detect?
We worry about that, but actually that's the one place we have reassurance, because the periodic table is a pretty complete set. The few things we're missing are extremely rare and unstable. And so even if they exist, they'll be in tiny quantities for a very brief period of time. And we have checked this. The composition, the kind of molecular and atomic composition of the solar system is very similar to the rest of the universe. So the actual distribution of elements, we know, we've tested. And so we know what the most likely molecules are. And if we expand that list like I have, we have a list of 16,367 molecules, for which we're still missing 15,000. But that's the list. Large, but importantly, finite.
And next, it says, relating to the last thing you said, do you think artificial intelligence could be deployed to help find life? If so, how?
Yeah, so one of the projects I'm working on tries to look at the 4% of the molecules that we do know about and try to train machine learning methods to find the others. The main problem here is that it's a very small training set and it's still pretty flawed. And so we end up replicating mistakes. But as these techniques improve and our data set improves, there's hope for using it. But right now it is just people.
All right, and then on that note, the next question is, what does the actual work of studying a molecule like phosphine look like?
Yes, so it's a lot of looking at a screen, using very powerful supercomputers across months of running code, and then trying to convince people in laboratories to do some measurements. And then we combine what we get from the measurements with what we get from the simulations on the computer to get something resembling the truth. The problem with this is that for most molecules, doing things in the lab sounds practical, but it's often really difficult, really dangerous, and sometimes illegal. Phosphine kills you in like 1,000 different ways very quickly, and so no one wants to measure it in the lab. And even if we can convince people to do it, really we need them to measure what that molecule looks like at all the temperatures and pressures that we might find in an alien planet. And that becomes really expensive and mostly impossible. So we need to use computer simulations, and trying to get both this lab work and this computer simulation to run across years is really hard.
All right, and the next two questions are pretty similar, so I'll kind of combine them. It is, does James Webb have a good chance of being able to discover a clear biosignature, and what other satellites and telescopes are going to help with that?
So JWST has started looking at atmospheres of planets. It has detected a few molecules on those planets, but it can't yet look at planets that are potentially habitable. And even if it could, it won't know for sure if a molecule that it detects is definitely that molecule or just a molecule that behaves similarly. So James Webb Telescope will not be able to be sure we found life, but they can detect molecules associated with life, just not provide us with that context that we need to be sure. Future telescopes, like I mentioned GMT and Ariel, will build this picture even better, but even they can't quite get us to a biosphere. But the decade that follows it, so the late 2030s, will have the Habitable Worlds Observatory, which is going to build on the technology of these telescopes to do exactly that.
Awesome, well that was all the questions. Thank you so much.
Thank you.
Right. Another round of applause for our wonderful presenter, Dr. Clara Sousa-Silva. And yeah, thank you again to our team in the theater, AV and Zach and Maya, and for testing out this new way of asking questions rather than trying to hand microphones over rows and rows of people. So if any of you do have tickets for the David Bowie show, you can stay in your seats if you'd like. Otherwise, please use the upper doors to exit. And we hope we'll see you back here on the 14th of December for Joel Green talking about From Hubble to the Webb Telescope. Thanks again, everybody.